Okay, so this is basically a recording of what happens when an Intel post gets made. Um, Although a bit changed because usually I'm not talking when I'm writing, but I'll try to make verbal what's going on in my brain. So first the key ingredients for an Intel blog post, what we need before beginning are our trustworthy Markdown editor, Tepora, here on the left. Tepora is a very nice Markdown editor. And that's what I use to write most of my blog posts. And the second thing we need is a cup of tea. In this case, it's mint tea. This is important. There is no coffee beans were harmed in making Nintil blog posts. So, well, there are various ways that I go about doing blog posts. So, for example, if you have read the longevity FAQ, that one took months to write. It was an extensive effort to collect notes and papers and annotate them, and I came up with this notion. I think it's maybe not this one, but I came up with a notion. Whatever. Well, I came up with a notion like a spreadsheet with all the papers and their summaries and things. But sometimes I just have some thoughts. Most of the things I think, even though other people find them interesting, I think that they're obvious. So usually I don't say most things I think. But for example, like this one, the unbuilding one. So some people like this one. It was a reply to Mark Andreessen's "It's time to build." And it was just some random thoughts I had, like some random connections that came to mind. So I just sat down and wrote it in one go. Nothing special. And people liked it. So yeah, sometimes it happens. Yeah. So this one, it was literally that. I just sat down and wrote it. There are as usually. So if you have, I've probably mentioned sometimes that I don't take notes, or usually. I mean, I on an ad hoc basis, on a case by case basis, I will take notes, but usually I don't. I just shovel stuff into my brain, and it works more or less well. And if not, I can just search my blog. Like if I link something here, I can just search for like I don't know, like longevity or something, and then if I'm like, oh, these are all the links and things about longevity in my blog, or I can search my Twitter in that case for the same reason. Okay, so what I wanted to write about today is an idea that's been going on around for a few days now, maybe a week, and right now I don't know exactly what form it's going to take. I more or less know that the one has come to write it. The way blog posts get made somehow is like there are various ideas bubbling up through over time. Sometimes just before going to sleep, like I just sit staring at the ceiling and just thinking about stuff, and then next day there is something else, and then it slowly ferments into something that more or less makes sense. But it's weird because I kind of know that usually it's time to write. It's a time for all different threads are ready to be compiled into one thing, but um, but I don't know exactly how it's going to do that. It's kind of like in an engineering problem, like you know that like physics tells you it's doable, but you don't know exactly how you're going to implement it. So here we are. Okay, so what is this thing going to be about? So I just call this innovation thinking, because I'm sometimes a strong believer in doing before thinking rather than thinking before doing. Sometimes just in the act of doing help you with the thinking, so you don't really have to think much of the title. Maybe I can think later, I can change this, but it doesn't make sense to spend lots of time thinking of this title. So it makes sense to just go ahead and write something. Okay, so what are the ideas here? So idea number one, I'm just going to use this is going to be the actual blog post, but I just want to use this as a scratch pad because it's a quick one. Okay, so idea number one here is the idea of discovery. Discovery can be random versus intentional. What do I mean by this? Well, rather than random, maybe brute force, maybe, perhaps. So what do I mean by this? Random, for example, would be you just happen, just find something. just come across something. You were not looking for a solution, breakthrough, etc. You were just found it. What's an example of this? A well example comes to mind. If I search whales here, they issue an article about cancer somewhere, maybe not. Here, there this, maybe not. Well, whales, cancer, universal. Yep, this is the one. Okay, so not that one, this one. Okay, so what do we have here? So they said that, well, this guy discovered a new type of killer T cell that hopes for one size fits all cancer therapy. It was quite impressive because it was a cancer therapy that can basically kill all cancers in mice and in humans. And it's very promising. And how did they find this? From what I remember from this thing, it was more or less random whether they find this thing. Where it was. I remember maybe the word bacteria was in near where I was thinking about. Oh yes, here maybe this is the one, or maybe this one. Which one will win? This one. Okay. Okay, so they were looking for immune cells that could fight bacteria, and they found a new type of T cell. So here's one example of a random finding. Like you were not looking for it, and lo and behold, you got a cancer cure. Intentional. Here is when you actively want to do something, and I guess an example would be the latitude price here. Well, not this one, and actually it was the longitude price, not the latitude price. Where's the OG one? Not this the new one. Where is the original one? Yes, the longitude was this, guys. Okay, so this the people said, well, I want you have to fix this. No, actually, this is not a good example because this is more about sure, in the cancer case, you also know that you also want to fix cancer. So this is not a good example. I guess intentional would be perhaps. So if you know about expansion microscopy, maybe this is an example. So the idea here is that when doing optical microscopy, you can just look at a sample through some lens and you get a magnified image. But also you can, at some point, you cannot keep going ahead because you cannot resolve super tiny images in optics, like features. So instead, one kind of galaxy brain move is to say this thing that these guys, among them Ed Boyden, said, well, we can make the sample bigger. It's like, oh, if you make the sample bigger, then same microscope, you get more resolution. Now, this doesn't sound very intentional, this is the presentation, but expansion microscopy. The idea here is that maybe from what I vaguely remember, and if not, we can maybe make up an explanation for an stylized way of doing this, would be to say, okay, we sit down and say, okay, our ultimate aim is to be able to image smaller features with optical microscopes. How do you do that? So in that case, you can say, okay, what are all the possible ways in which you can advance this technique? So here you can have some heuristics. So for example, maybe take an assumption, and then flip it. So here you say, okay, well, an assumption in microscopy is that you have the thing, you look at the thing, and usually you think about how to improve your instrument, but not necessarily how to change the thing you're looking at. So in this case, you could say, oh, what if instead of making quote the light bigger, or like in a virtual way with optics, we make the actual thing bigger? It's like, oh yeah, I mean, it sounds obvious in retrospective, but this thing took a while to be discovered. You could also argue here that another thing you could say, okay, you could use physical constraints. An example here, well, I guess it's the very sample bias, because these are progress I've kind of looked at. Marblestone, scalable neural recording, blah. Thanks Google for spell checking me. Right, so this paper, the idea is that, well, if the tiny brain thing to do with brains is to record a neuron or to do like a Neuralink thing. Here is, well, what would it take every year? What would it take to measure all the neurons at millisecond resolution? And it's like, yeah, great. Okay, so can we actually do this? Is this feasible? Well, so we can then go and say, okay, what could we use for this? We can say, well, we can use infrared light, ultrasounds, something called molecular recording, electrodes, or MRI. There are various ways. But the important here is that we can make some estimates of, for example, energy dissipation. We know that if we put too much energy in the brain, you're going to hit it, and that's not good for the neurons. So you can make all sorts of calculations to kind of constrain the area that you have to play with. Similarly, in I guess you have the Landauer limit. This, well, maybe not limited, but limit. This idea that there is a minimum amount of energy that a computation required. Maybe Landauer. So this might say, well, technically, maybe we can pull this YouTube presentation on real recording. No, real recording. Where is it? Looking at there. Neural recording. So what was I thinking about? Yes, reversal computing actually. Okay, so this stuff. This is one I watched, so we can put it to blah like that. Okay, so the idea with this one is that we know that we are far from the theoretical minimum. We know that we are far from the minimum of this minimum. We are using a lot of energy to do computation. And this thing says, well, physics doesn't prohibit you from getting up to this point, and we are all the way here, up there. So, it's not that we cannot. So now it's we're thinking, well, how can we get there? If we know that there is no obvious a priori reason to think that we cannot go up to here, then why not? And so these people thought about this way. It's called reversal computing, and the idea is that you can actually prove that you can do some, at least in an idealized way, you can do some computations without spending any energy, and I think you only use energy if you are erasing or deleting information, because that's what makes it non-reversible, because you cannot recover the prior state of the system. Okay, so this I guess like the galaxy brain. I never really like this thing, the galaxy brain meme, but this is kind of like a triumph of thinking, sort of things. This is where you methodically go and map the field and decide either what the solution is or what the path towards a solution might be. Then we have the brute force, machine learning, basically. So in machine learning, we say, well, this we don't really need to do thinking, we can just let the neural network learn it. So, for example, in one way, if you want to have self-driving cars, we need to say, okay, we're going to have one module to say, okay, this is the road, and then this is a car, and so on and so forth. But we can say, well, this is a reward function, and this is an architecture, and then you train it, done. You don't have to think, just, or rather, the thinking goes, maybe we can use this, thinking goes to the meta level. In this case, you're not thinking about the thing itself, but how to design a system that solves the object level problem that you had in the first place. Okay, so number, I guess, 2, it's kind of like the key idea. The second thing is that can we systematize intentional discovery? Why? Well, it would be nice if this kind of thinking can be made easier, but so to speak, breakthroughs at scale. So instead of trying to just think in the abstract, you have a step-by-step guide that tells you what to pay attention to, and you can call this at risk of sounding too Silicon Valley-esque, like a mental model for breakthroughs. And of course, like here I'm saying that I'm the first one noticing this, of course, and ideally one wants to go and see if someone else has already come up with ideas for this. In this one, though, I want to present is a quick, more or less quick thoughts about the way I see it. In a way, untainted by prior thoughts from other people, and then maybe in the same blog post, or maybe in a later, maybe I will hint in this one at some prior research that people have done in this regard, and then maybe in the next one I will go deeper into that, or maybe not. Okay, so can we systematize intentional discovery? Can we make this kind of thinking accessible to everyone and make clear? Okay, the next one is brute force. Are these three things actually different? Why? Well, if you think about it, there is a space of solutions for problems, ultimately. And it's a search problem. You have to know exactly what you want. In the random case, you were not looking for it. You just stumble upon some solution. That's not ideal, but maybe it can be that not. Of course, is the whole point of that. Not looking for X can be better at learning about X. This is a bit of a weird thing, but this is kind of the idea that in science, learning about some field can give insight in a different field. So suppose that all you do is to focus on let's say cancer biology the way we currently conceive of it, and you don't do other things. I don't know. I don't really buy this. Well, again, so to fully explain this idea that people say, well, you look at this in this sort of field, and then or you do some NASA stuff, and then you find with some spin-off in this sort of field. Well, you can always say, well, couldn't you just do the research in the field you did discover in the first place? Like sure, like doing large particle colliders will probably get some improvements in material science, but you could just research material science in the first place. Unless, well, you could say, well, unless there is some kind of regularization effect going on here, so maybe it forces you to do some, I don't know, probably not. Okay, so search space and random. Okay, but brute force and intentional. So intentional, of course, you have the search space, and you try to say, well, historically, these are the ways in which we have carved this search space in the past for different kind of problems, and we have arrived at solutions, at breakthroughs. Maybe I should define what breakthroughs are, or maybe a working definition for this post. It's I guess the idea I have in mind is something that I don't know if what is mentioned. Something that is significant in some way that may be obvious in retrospective, but was hard to conceive from the prior paradigm. There is not a breakthrough because I guess breakthrough. What do people say when they mean breakthrough? Well, not this movie. Science, I guess. Yeah, significant development scientific research. What is that? Breakthrough of the year. Yeah, we can. Yeah, you said like milestones, like things that maybe took a lot of effort to get to. But I guess this is more macro what I'm thinking. So maybe micro breakthroughs perhaps is a better term. Like I guess that expansion microscopy is not just like, oh, we can actually make the thing bigger. That's I guess like the kernel of the idea, like the thing that enables the later development. So I guess in that case, it's not only that, but also realizing that you need some kind of polymer and to get isotropic expansion of the sample and spectroscopy. So you need more work in there, or you could also argue that in the Manhattan Project, the kernel or the core idea was well, that you could get and you could make weapons out of nuclear fission, and around that you can build like layers of engineering and various other advances you have to make in order to get to the actual nuclear weapon at the end. So I guess that what I want to think here is more at the micro level, as in very atomic or small ideas that, yes, maybe small, what small idea I even mean? Small idea that maybe it could be an actual breakthrough. Like, I guess in a way, oh, and this, I mean, this is another point, the fractality of this. What do I mean by this? Well, it's like, yeah, well, general relativity, you could call this a breakthrough, but then how do we get there, or what ideas enable like Einstein to get to the point from where he could see general relativity? Yes, we just wanted to get. I guess that the moment I'm trying to capture here is you. There is a problem that you want to solve, and you don't know how to solve it. Like, you have thought about the usual ways to solve this thing, and you're stuck. This, of course, happens in science frequently, because science is about creating new knowledge. It's not just about describing or cataloging what we already know, or repackaging that, but also expanding the frontiers of what we know. So if for example, you may say like, oh, like, we want to cure aging, we know that, well, there is no in principle physical reason why we cannot do that, but then it's like, okay, now how did you do that then? And then you go into, okay, well, let's pick one problem within aging. One problem within aging is that there is an accumulation of certain kind of molecular garbage that sometimes goes by the names of lipofuscin. Lipofuscin is so called because it's kind of like fluorescent in some assay, but it's not just lipofuscin. Here's like lipofuscin in there. So basically, the lysosome cannot digest these things, and they stick there, and apparently it causes aging somehow. Okay, so then the question is, how do we get rid of this stuff? Well, that's the problem. It has not done before, hasn't been done before, and so we're in this moment we don't know, and then at some later point we are at the breakthrough stage where we either have a solution or have a promising avenue for a solution. Yes, I guess that promising avenue is something that may yield results or may not, but at least it's a way forward from the point of being stuck. Okay, so in this case, the solution as it happens, maybe we can talk about that. Lipofuscin sense. Lipofuscin sense. Yeah, so the idea here is to get some enzymes into the lysosome that can actually clear this stuff. I don't know if we have. Well, yes, of course. Like, this works for everything. No surprise there. Didn't mention the enzyme thing here, I think. Interesting topic for a blog post, like to see what exactly works for reducing the accumulation of lipofuscin in the brain. Like, you can get a galaxy brain if you have lots of this stuff in your brain. You will have a tiny brain. Yes. So yes, in this case, we get enzymes into these things. Okay, and then that's the avenue. Then that kind of unlocks not a solution but further ideas. Then we get to, okay, how do you get those enzymes in there? Will it be a small molecule? Will it be like gene therapy? Do we genetically engineer lysosomes, cells, to produce lysosomes that have these enzymes? We also think that we also can expand our thinking, and this goes into like these intentional ways. enzymes examples from other species, which is kind of like what inspired this. We say, okay, is there anything like this that happens somewhere else? I guess it's kind of like a lazy, in a way of innovating. You say, okay, this works here, or I need a problem. I have this problem here. This problem looks like this other problem. So, and this problem is solved within this other species. So I can just take this enzyme from here and then put it in here, and boom, works. It's like we have this guy, like, oh, we want to make things fluoresce. Well, we have this stuff, the green fluorescent protein, that was extracted from some random jellyfish, and now we can make things and brains into actual shiny brains. These are some what is even this? Granular cells. And we can also make them in funny colors too. But that's the idea. We can just see if it exists somewhere else in nature and take it. If not, we may have to do some thinking. Or even, okay, suppose we find that this works in a bacteria. Fine. So we could say, can we just take the gene in the bacteria and put it in a human one? Or use something like an AAV, an associated adenovirus, this guy. Use something like this to get them into cells. This funny virus, it gets into the cell and it doesn't enter into the genome, so it's kind of funny because you can put a gene in there, it goes into the cell and it makes copies of itself. Because biology is kind of messy, you just put some of these enzymes out there, and if they're done in the right way, they will just get to where they need to go. And that's the problem, of course, that it's like, well, but that's another problem, that you then get into the next phase of thinking. You're like, okay, let's suppose that in this case, we have a problem, which is get rid of lipofuscin. We know that this bacteria does it with this gene, and then it's like, okay, what if we just put the gene in a cell? What can happen? Well, maybe the enzyme is going to fuck up something else. Maybe it just works. Maybe, I don't know. Maybe it doesn't harm the cell, but doesn't do anything. In which case we can do, okay, why? Why is it not doing that? Is it that it's the enzyme being degraded because it's recognized as a foreign enzyme? Is it because there is some regulatory pathway that's inhibiting somehow that gene or something? And so we can into thinking that, okay, once we have identified, well, if it's a solution, boom, solution, next problem. If we have not identified what the problem is, if we have not identified if we have not identified the actual solutioning window, then we can then go to the next step and say, okay, it's not working. Why not? Because the enzyme isn't getting to the lysosome, it's getting degraded somewhere in the cell. Fine, okay. Why is it not getting into the lysosome? That's the next question. And at that point, we don't know. So we go and say, okay, let's try to do some 3D molecular recording magic to see what's going on with the enzyme, and we find out that we know that enzymes get into the lysosome when there's some protein that gets attached to them and puts them in there, but maybe those proteins are not taking this enzyme into there because it has some weird shape. Okay, then the problem becomes, how do you get the shape that can get the enzyme into the lysosome? Okay, that's one way. And then, okay, so then the problem is, the problem becomes kind of difficult because you want a similar function to the function in the enzyme, but such that it has the right shape to be put into the lysosome. So that then the problem becomes, okay, these are more or less the shapes that these proteins need to get into the lysosome, and you can also look in nature. It's like, oh, like this enzyme has these analogs in other species. So then you can look at them and use that to inspire some modeling, and then maybe you can, at this point, just brute force the final step of the solution. In this case, you have like hundreds of different parallel like tests and assays where you are testing um, gene expression or gene therapies, lots of kinds in different cell cultures until one of them, so it happens that that one codes for a protein that gets into the lysosome and breaks down the thing and problem solved. So chains. In this case, we have coupled I guess the coupling various mechanisms. Thinking takes place inside some frame and background assumptions. An example is the can light go through the brain. So okay, so if you want to get images of inside of the brain, you wouldn't think of using light, because light is like, oh, it's light, like you have the skull and skin and stuff. Surely you cannot shine light through a brain, but maybe you can. So maybe I can find, yes. So you can shine light through the skull. And it's like, oh, yes, that makes sense, right? Like, after all, I can take a lantern, put it in here, and it kind of maybe, well, if it's powerful enough, it can shine through your hand. So that's something. Okay, well, and then, I guess, yes. Okay, so you could get, how do you get to the point where you think of using light? Maybe the idea just pops in your mind. This is a random idea. Or you have gone through this process of, I guess, the discovery. Oh, maybe always engineer discovery. If you want to get sassy, we can call it mass-produced discovery, because the versus the organic, gluten-free, keto, paleo discovery. This is the one where it's like you get the apple on Newton's head and you get this idea suddenly in a very innocent way, instead of painstakingly enumerating things. Okay, two things here. Thing number one. This thing I've been talking about enumerating possible alternatives, sounds like brute force. You could argue that here the things you look at is not brute force, like you are not literally thinking, oh, can we use bacon to look at neurons? I don't know, what would that even mean? You're thinking about, I guess, reasonable things within that domain. We can also say that maybe brute force. So if you're searching at random, if you're searching by brute force through some domain, then you will maybe find some answer, but that answer you will not know what the answer looks like or when you're going to get it. So it's random in that sense. So in that sense, brute force solutions are effectively random. So you just happen to come across a solution, but there's still a difference, which is that in the you can still be looking for a solution versus happening upon one. Like Newton was kind of thinking about gravitation in general, but at least allegedly, then the story goes that the Apple moment was when it all clicked. So I think in that case, that's a case of, yeah, that's the thing that that you could say that he was exploring the space of answers to the problem of general gravitation. And the Apple thing, which is like a bit of noise that just triggered that last insight. So I guess it sounds intellectually satisfying to argue that all these things are the same in some sense. But are they though? Also argue the scientific community is this at large. Like you get random discoveries, of course, like across fields. You also have you want to make this claim? I don't know. Maybe brute force is that you have lots of people working on science. Maybe. I don't know. Paleo. Yeah. So this random thing doesn't sound very satisfying because it sounds like, oh, it just happens. And it doesn't just happen. Like you are not like if you haven't been thinking about related matters, you usually don't like, I don't know, let's take the quaternions, you know. So quaternions famously were this bridge, this funny inscription with this Sir William Rowan Hamilton was going around and he wrote the formula there. Let me see if I can find the history for this thing. Yeah, so he was thinking about complex numbers and things, and then he was walking around Royal Canal, and then he got a solution. So he saw, that's the thing. So he had been like thinking about the issue, and then a solution happened at that point. Does this really count at random? Or is this like the brain is kind of doing brute force search in some way, or like random search in some sense? So yes, I think that it is true that effectively, actually it's the opposite. Random discoveries are brute force, both within same, like it's both you that like through time you're kind of thinking, or in the background like you're getting random new ideas and that and new associations. That's just how the brain works. You just get these random things going on. But then you also get other people doing the same thing. And brute force, I guess they're like brain powered brute force, actually. Not very efficient, but they just happen. Which then, of course, leads to the question of, okay, like you don't want these things to just happen, you want to rigorously get to them, which is the whole point of the intentional thing. Okay, so we can reduce, I guess this is a good step. Random is actually a brute force. Maybe random is that's not the right word. Maybe what's the a good word for this? Happenstance? Well, we'll get to that thinking later. As I say, let's do it and think later. Okay. And then, so we're then left with two things. We can actually think through and enumerate, or you can literally search everything. But even here, as it said, yes, intention is like brute force. So you're just brute forcing. It's brute force with priors. That's what intentional is. So at the end, you're just sweeping over a domain in a reasonable way, and getting to a solution. Yeah, I think that this can be. I can probably start to write now with some of this into shape. But before, I guess we can go to one concrete example. Okay, so how long have we been going? Yeah, I don't know. Well, maybe I guess 2 hours and a half. Like, I don't know who's even going to be watching this. Well, good luck. Let's do a quick Twitter search to see that the memes continue flowing. They do. So let's figure that. Well, I've been kind of given one vague example of with the enzyme and the lipofuscin thing, how you would go about solving a problem in a structured way. And as I said, is maybe this is the way everyone kind of does it, and that may well be true. Or I don't know if because you can also solve problems by just stare at a problem for a while and then boom, you get a solution. That happens. Like sometimes you just look at something, just try to do it and try to do it in a kind of mindless way, and then at some point, boom, the solution comes and you do it. But that doesn't seem like the best way. I mean, I remember being in a situation when I was in college. Some things that went into my one famously recon paper, multi-body. This one, which I think I cannot even access, but this paper with it, if it wants to load. Jonathan Blow is very correct that things are slow. Yeah, so that's me. So this paper with it, so some of that at some point at the beginning I was like, I don't know how to solve this. I will just like stare at some weird algebra, and then next day stare at some weird algebra until like, oh, this is the way, and it clicks into place. That seems like a bit masochistic. Like imagine we had something like the Matrix cookbook, which was very helpful, but I didn't know the cookbook back then. So you had this cookbook, and you have all these. Come on, cookbook, you can do it. Oh. Yeah. Yeah, so you have all these matrix identities that you can use. So imagine having like, oh, like have you tried using this identity or this thing? Like having like a clippy that says, oh, have you thought about using the Frobenius norm in this problem or whatever? Yeah. Okay, so what would be one problem here? Because I guess you can go very general. You can talk about the generalized measurement problem. So the generalized measurement problem. I don't know. Maybe this is too vague. This is about how to measure literally everything. What steps would you follow when you want to measure something? I'm writing about that one because I wrote about it. So maybe, yes, let me try to find, so this is in a context of some emails that you don't necessarily need to see, but it involved the word multiplex, so we can search that. Yes, I think I found it. Okay, so how to solve the generalized measurement problems. Generalized measurement problem. Generalized problem is measuring property X, system Y. This thing is complaining about spelling. Let's be British. British mode activated. Okay, so you want to measure something. Sure. And the reason this is a problem is because it's not solved yet. So how do you solve it? Okay, what things can you do? Thing number one, change the measurand. So maybe you really care about z and x is a mere is related. Or maybe x was a proxy to z, which is sorry, maybe measure a proxy of x, which is easier to measure. And this is an example of fMRI. Like fMRI, you are not measuring electric activity, you are measuring changes of, like, I think it's oxygen concentration or something in the, it's oxygen, right? Yeah. In the brain instead of activity as such. We're saying, well, I mean, if there's activity, there's maybe more oxygen, more blood flow, so you can use this. Yeah. You can also make the system easier to measure. That's another thing. For example, in expansion microscopy, you can make the system bigger, and that makes it easier to measure. You can also change the context. Change the context of the system. So if you want to measure something, you can take it to zero gravity. You can measure in vitro instead of in vivo. Just put it somewhere nice where you can measure it. What else do we have here? You have, like, just improve the instrument you were previously using, like well, optics itself. Like, you have been doing optics, optical microscopes, and you just keep doing the same thing, just better lenses, and then and I guess the difference between one of these ones and one of these ones is just like the new ones have more resolution, but the idea is the same. It's a super, I don't know, it's this thing, I think. Yeah, super resolution, I don't know. Yeah. Okay. Then you can, another thing I can think of is that maybe if the problem is getting the data out of the system, you can multiplex. This is of that. Multiplexing, this is improved transmission of data between the system and the instrument. Well, and this is not really multiplexing. Multiplexing is doing, well, in biology people talk about multiplexing like doing various measures at once, or measuring multiple channels. But well, in a way, if it's more data, I don't know. You can also, like, measure multiple times, and then aggregate. This idea, for example, like modern so-called NGS sequencing is basically that. Like, instead of, you don't take the genome and go one by one all the bases and look at them, you instead, this is if I can find, yeah, here's one, a good one. You instead break the genome in chunks, and then you align the chunks, and so you get, like, in a way, lossier, smaller measurements, and from this you reconstruct the thing you really wanted and aggregate them later, like here's sequencing. You can also get the system to measure itself somehow, or maybe rather, or like just change the system. Well, maybe just change the system. Well, I guess it's a an example of this optogenetics, which is the same guy. He's like, I call this boy the nicest system. I don't know if this makes sense. Make the system record itself. That's the next galaxy brain. It's like, what? Well, you can do it in a computer, and also, I guess, molecular recording is the one that comes to mind here. This is the idea, but again, it's from the this one. The idea here is that you have the neurons have a quote ticker tape, and they are recording themselves in let's see, this local storage of data molecular substrates. A neural engineer to write a record of its own temporary activity onto a biological macromolecule. So you're just, in addition to doing its thing, like the neuron is now also recording itself. So that, I mean, it's kind of difficult to do, but that's the idea. Okay. What else can we think? What other? This is not. I guess this is not the final form of like the handbook of making breakthroughs. It's kind of like a random one example that I thought once. Yeah, that's it. What other ones can we think of? Again, here this is another example. In trying to write this thing, it's kind of in a way it's like a breakthrough, because it's like, I know that you can do this. I don't know exactly how, and I don't have an exact way of making this thing in this particular case. And in a way, I'm trying to make the thing that's the general approach to solving these kind of problems or thinking through them. So instead, I'm doing brute search. I'm literally staring. That's how ideas happen, right? Like you just stare at something, and then you kind of let your mind wander, and then ideas happen. So let's do that. And also, it's not just like it's happening. Like you can just read through this list, thinking what similarities are there, what things are different. Let's see if there is something in between these things that actually could be another one, and we'll see. I guess I'll come up with one more or two more. That's a funny one that you know that you can probably come up with more, but you don't know exactly which ones. Oh, this is actually the same. I guess that we can also add quantum weak measurements, which is the same idea, but in quantum mechanics. Blah. Create the information not on average, and then just aggregate over them. Okay. What other ways? So we have the system. We can put it somewhere else. We can keep doing what we're doing. We can make it easier to measure. Well, this intrinsically maybe, whatever that means. Transmission. Well, this sounds kind of lazy. It was like, oh, I just improved the instrument, but well, this because I don't really know that much optics. So maybe we can take this out. Yes, so we are measuring data goes out, so that's the multiplexing is improving the way data is getting out. Then so we can change the thing. I mean, these are of course very extremely generic categories. And again, these two, just the context. Well, I guess you can think of like the thing and the surroundings of the thing. So these two are legitimate. This one, what would be like this one? Well, there's of course like the idea of not measuring it in the first place, which kind of circumvents the problem, right? Like, as to say, there are no bugs if there is no code, there are no problems, or there are no solutions to be found if there are no problems. Um, I guess also a benefit of maybe doing this thing with other people is that even though you both are doing brute force search, you can explore different areas of space and come up with like various ideas and like influence each other, so like in unexpected ways. Um, mm, mm, okay, we can think of maybe historical examples, like thinking of like fish or fluorescent assays, like. Um, but this one kind of counts as Boyden-Ice. Yeah, it's like yeah, it's probably a case of Boyden-Ice the system, or maybe changing the measurand. I guess you need to sometimes do this to that. Yeah, like here you say, okay, I want to look at fluorescence instead of expression, which is just I guess concentration, and then how do I do this? Do this. Well, of course, like I'm not considering like the economics of this, because you could say, well, like this may be expensive, and then we talk about like making things parallel, making things more efficient, and so on. Maybe making things well faster, but it doesn't sound like an approach. It's more of a concrete case solution you would arrive at from other. Okay, let's settle on the 6. I said that you could get. Maybe we cannot. Maybe this is it. Now, okay, we have said that we either conceptually change what we're looking at. We look at a different thing. We change this thing. We change what the thing is. Take more data out or improve the way that it's getting out. We do multiple measurements, or we move the recording from to being as an OR system into the system itself in a way, like collapsing both things. What other things? I mean, you can probably draw these kind of various things. But yeah. Okay, so maybe we can begin to write. One more check for the memes. Okay, so what do we want to say? Like, I guess that some people say, oh, your article should have a point or something. And I'm like, I just have things to say, but I have to be put out of my head so that I can think of something else. So, where do we begin? I guess that there are like various ways, like stereotypical Nintil ways of starting articles. I think I remember I've done like, there's like, suppose, thing that. Oh, what's this one? No. Okay, let's say, well, let's think, suppose you want to solve a problem. The problem is not solved. Well, that's kind of redundant, but it's funny to say. The problem is not solved yet, because, you know, you don't see how we forward. Or problems, well, I'd rather, let's say, a problem. When problem solving can be one of two states. Well, there's a third state which the problem is solved, but you can be stuck, or exploring promising avenues. A promising path forwards. Yeah, might work. So it's up to stress if that's the right way. In this case, maybe in science, this might be akin to regular science, where we know maybe or one-to-end science, or something like that. If we are stuck though, oh, I guess I think solving is about the process of going from being stuck to not being stuck. I guess going from being stuck to having a path forward. Science. By 0 to 1, I mean something that doesn't, that maybe is how to see from a prior conceptual framework the assumptions we have. Some parentheses. That's a great problem. Like, I want to use parentheses. I want to use size. But perhaps after the fact they become obvious. That's kind of like the happens. There might be 3 ways of going about doing this. Well, one is, we said, is one is random, randomly getting them unstuck. You know how this works. I don't know. Context. Play a bunch of photos. Why? Okay, then we can systematically getting unstuck. It's kind of like what we said earlier. I guess we can start to delete stuff from here. So what do we have here? Oh yes, an example of this would be this cure for cancer. Well, not cure, please. This potential okay, so there we go. We said we don't really like this, so this is done. It's not really getting stuck. I think I have an example, but I don't know if I can mention it. Oh, this is not nice. So let's say instead. Solution to would be reversible computing, and we can link this. We can link to Landauer's principle here. Principle, yeah, principle. What's this one? This one in there, and then I think this one comes later. Reversible computing, and we can put this here. Okay. Brute forcing. So I think of Mel. Well, it's not really exactly. I guess like there is this 4 square problem or something like that. It's not this thing. Color theorem, proof exhaustion. Oh yes, proof exhaustion. That's the one. Interesting. Oh, I didn't know this one. Okay. Yeah, so check one. So just artificial solutions. We see these. Theorem, or maybe in high throughput, maybe I guess maybe in some high throughput screens. things. Compounds. I guess you keep testing until one works. I guess that ML is an example of this. Because, well, I mean, that's, well, I guess it's ML. ML is an example of this too. But why? Seems like it's a way of brute forcing. Or we can say maybe just with word in as much or in so much as as an example of this, in so much as we are not thinking directly of the problem, but instead delegating the thinking to a powerful system, or to a more powerful system, because it's powerful, a powerful system that can do search in a more efficient way, while we instead think about a system. Okay. Yeah, I don't want to mention expression microscopy here. Maybe. Yes, over here. Maybe we can put this at first. Well, I already mentioned this. Yeah. Okay, so in the field is then. I guess maybe we can use the gray little sensory, because that's how it was found. Oh, this is. Oh, okay, so well, yeah, the story here is that over the gray was thinking that, oh, well, graveyards are shining with little scenes, so there are probably organisms eating them. Maybe you can mention it later. Let's get first to. We'll also mention this at the beginning. Processing avenue resolution. Yeah, okay, let's do this one, I guess, comes first. So, actually, well, I guess underscore is, yeah, I just when this happened to me. Well, I guess next problem. Talking about problems in terms of like problems are things you get stuck with. Like I don't know if you have to this do a website. That's not a problem in that sense because like it's kind of well trodden. It's a solved issue. It's not something that requires change in the way you see things or something. Yeah. So we have said that we'll say that a guided form of brute force. Priors. Yeah, you can think of that. Brute force, maybe. Yeah, but reset these. I think I'll reset these ones. Yeah, I think this article is going to be like 1,000, I guess, 1,000 words long or something like that. With priors if you wish. We'll reset this by the way, and these ones are kind of. Yeah, so I guess that we have made that point. Why it doesn't matter they are the same thing, I don't know, but that's it. So yeah, let's delete this stuff. I had to write this even free. Yeah, that sounds nice. Okay, so that's done. The brain one. Yeah, all of the concrete examples. Well, I mean, at this point I can just probably end. I mean, this is getting, I guess, quite long. Yeah, an hour 20. So yeah, so you guys get the idea of what I've been saying here. And this is going to just be this plus a bit more of an elaboration. Maybe we'll change something else. And that's it. Well, thanks for watching. And I don't know if this is interesting or useful, but there it is.